Hi everyone, this is a conceptual understanding video to discuss a phenomenon we see in chemistry often known as buffers. So let's imagine an experiment where we measured the pH initially of 5 milliliters of deionized water and 5 milliliters of a mixture of acetic acid and sodium acetate. In other words, a solution of an acid, a weak acid, and additionally added to that the ionic compound containing its conjugate base. What we see is that originally the deionized water has a pH of 7. If we add a milliliter of dilute hydrochloric acid, that pH drops to 3.1. If we take another sample of the 5 milliliter deionized water and we add a milliliter of dilute sodium hydroxide, the pH jumps up to almost 11. All right, so upon addition of HCl, we see a pH drop by 4 pH points. On the addition of a base, we see it go up by about 4 pH points. On the other hand, our mixture of acetic acid and sodium acetate changes very little in pH. It's initially about 4.7. It goes down to about 4.5 with the addition of HCl, and it goes up to about 4.8 with the addition of sodium hydroxide. So what we see is that the pH of the water is very susceptible to an addition of either acid or base, but the pH of our sodium acetate acetic acid solution stays very nearly the same in pH. So what's going on? Well, what's happening here is a phenomenon known as buffers, and buffers are generally found to contain two things. They contain a weak acid, and they contain an ionic compound, also known as a salt, containing the conjugate base of that weak acid. So in our example that we just looked at, we have two things. We have acetic acid plus we have sodium acetate. That will give us a solution that is a buffer. Another example might be if we had hydrofluoric acid plus lithium fluoride. That would also give us a buffer solution because HF is a weak acid and LiF is an ionic compound containing the conjugate base. Another example would be if we had hypochlorous acid plus potassium hypochlorite. That would also give us a buffer. All of these would fit our definitions of buffers. These would, if we mixed these solutions together, we would have a pH, we would have a solution that would have a pH that was resistant to change with addition of acid and base. Now, things that are not buffers are going to be anything that doesn't meet this criteria. So, for example, if you had a strong acid plus an ionic compound containing its conjugate base, that would not form a buffer solution. All right? Why? Because that's a strong acid. We know that from our list of strong acids. Even though it's an acid plus its ionic compound containing the conjugate base, that doesn't meet the criterion. Also, if we had a weak acid, like acetic acid, and we failed to add something containing its conjugate base. So if we had acetic acid plus sodium chloride, chloride is not the conjugate base of this acid. We would need to have had acetate as we had in the above example. So this is a case where we have to have both the weak acid and the conjugate base present in solution, or otherwise the solution is not going to meet the criterion to be a buffer solution. Now, why is this the magic combination? Why is a weak acid and a conjugate base the combination that leads to buffering? Well, the reason for that goes back to Le Chatelier's principle. Remember that Le Chatelier's principle says that anytime we have an equilibrium, that the system will shift as though it is trying to undo the stress that we, the outside chemists, have applied to it. So in the case of sodium acetate and acetic acid, we think of it not as a reaction between the two, but as the equilibrium situation present that is created by the dissociation of the weak acid. When we have both the weak acid and the conjugate base present, what happens is that, let's say we add some acid. So if you add HCl to this, what does that do? Well, remember, HCl dissociates completely because it's a strong acid, and that creates additional H plus ions in the solution. By increasing the H plus ion concentration by Le Chatelier's principle, increasing the H plus drives the reaction in reverse and uses up some of that H plus. That's only possible if you have plenty of extra conjugate base present. That's why you have to have acid and conjugate base present in order to have a buffer. So conversely, if you were to add sodium hydroxide to this solution or any other strong base, remember that the hydroxide is going to react most strongly with the H plus and make water. Well, what's that going to do to our equilibrium up here? What that's going to do is it's going to reduce the H plus concentration. Le Chatelier's principle says if you remove something from the product side, the reaction will proceed in the forward direction to replace it. And so that's going to put those H plus ions back into solution that you just removed by reaction with the hydroxide. When the reaction shifts forward, it replaces those H plus ions, and the pH has very little change. In a subsequent video, we'll go over how to deal with the pH of buffers, and we'll talk about what happens when you add too much acid and too much base. Thanks.